we will be building, or let us say, making our electrical design. This is stipulated in our Philippine Electrical Code, and even our dear chairman of the Board of Electrical Engineering, Sir Mapili, not encourage us, but hopefully this is imposed na, no? Kaning in every electrical system design, there should be short circuit analysis and voltage drop calculation that is presented. And of course, for those who are have the intention of applying for professional electrical engineering, kaning ato ang pag-apply for PEE, you will need very basic now short circuit analysis and voltage drop calculation. Must na gyud ni siya, no? Though there are other topics in electrical or in power system that is included, but parang basic na ito, dapat mayroon talagang short circuit analysis or voltage drop calculation. Okay, participation na naman, no? Kunting ano lang, no? So again, there is another survey here. This calls on what is this? How to ilalagay lang muna natin sa ano, ha, sandali lang, para at least madali sa inyo ang pag-answer. Ilagay ko sa chat. So this is again a survey on fault. Ano ba yung kadalasan na type of fault that will occur in a distribution system? So participation na naman. So kunti lang, pampalipas oras. Kung ilalagay natin dito, ito yung tanong. In one word, ano ba ito? Mali. Sorry. So meron kayong pwedeng okay. Which of the following fault occurs most in a distribution network? So ito ba three-phase fault, single line to ground, or line to line? So ito yung ipopost ko sa inyo, and kung pwede makapag-answer kayo niyan, no? So for those who cannot, I think diretso na ito, pero pag hindi kayo magawa, ito lang ang code na ilalagay natin. But I think you can directly place your answer there. So this is the course outline, and for the introduction, any failure which interferes with the normal flow of current. So most faults in the case of transmission lines are caused by lightning, which results in flashover of insulators. Now, single line to ground fault, 70 to 80% of distribution line faults. So parang ito na yung sagot, no? And we will see ano yung sagot natin, no? Roughly 5% of all faults involves three phases known or as three-phase fault. Other types of faults are line to line and double line to ground. So kadalasan na mangyari itong single line to ground fault, we are very familiar with this. Example like trees touch during storm or rainy days, when it touches the one of our bare distribution lines, overhead lines, no? So that is a typical example. And also the fault analysis of a power system is required in order to provide information for the selection of switchgear, seating relays, and the stability of system operation. So ito yung pag-determine natin yung sa protection scheme, yung sa circuit breaker. Ano ba yung common natin na makikita or uh, we can hear yung kiloampere interrupting capacity, no, or KAIC natin. Then sa setting of relays, this will be another topic. This will be yung sa ano na natin, coordination, yung sa setting ng mga relays natin, at saka as part of, as a starting point of stability of a system, stability of system operation, we need data from, or we need the result from our fault study. So dito lang tayo sa protection ng CB, yung pagdedetermine ng KAIC. This is the intention of this lecture. So digital computers are used effectively in the calculation of three-phase short circuit at various points in the system. Try kong makita kung may sumasagot ba sa ano natin, no? So titingnan natin kung tama ba yung answer natin. Most of the time, ang makikita natin is the single wow, 79%. So ito ang parang makikita natin na nagja-jive ba, no? Ang knowledge natin nagja-jive sa information na nalaman natin. And of course, meron talagang ano siya, parang validation ng mga ginagawa natin. So at least I am very grateful sa interaction ninyo. Thank you very much for having set a time for answering the question. Thank you. And we are correct, no? We are indeed correct sa ano natin. Ito ang kadalasan na mag-o-occur na fault natin sa ating mga linya. So for the assumption here, sa analysis natin, mahirap kasi itong balance lang yung ano natin. All sources are balanced and equal in magnitude and phase. For simplicity, sa when we have analyzed our system, then sources will be represented by the Thevenin's voltage prior to fault at the fault point. And usually for simplicity din, parang ginagawa natin na default ang per unit value ng voltage natin as 1.0 para mas simplify. Now, when you will be taking details of this, ang ginagawa talaga, sinusolve talaga yung open circuit voltage at the fault point, no? Then for large systems, this can be represented by an infinite bus bar, no? That's it with the 1.0 default per unit voltage. Then transformers are on nominal top position. Sometimes resistance are negligible compared to reactances, but for let us say for commercial, industrial system, we have to include the resistance. Distribution or transmission lines are assumed fully transposed, and all phases have same impedance. Load currents are negligible compared to fault currents. So this now sometimes we will be neglecting the load, no? Except for instances, especially in the industries, the presence of induction motors, no? Or ang load natin kadalasan mga motors. So dili na siya pwede i-neglect, no? We cannot neglect that one. There is a method, systematic way of determining or calculating the fault using the Z-bus, but we will not be tackling this one. We will be discussing more solely on a simplified approach of determining the shunt faults, particularly in distribution network. Very simple indeed kasi radial type lang siya, no? And even in some even in the industry or in the commercial system, ganun din ang mangyari, radial lang siya. So ang analysis is not so complicated. So dito, we limit our study on the shunt fault. Though, sa bagong ano ngayon, sana hindi kung pwede lang sana, no? Hindi na lang natin, there is also another type of fault that is part in the analysis. We have the series fault, but here in our discussion, we will just focus on the shunt faults. And 4 of them will be tackled here. One is the symmetrical fault. We call this the three-phase fault. And then the asymmetrical fault. This is not symmetrical. We have the single line to ground fault, line to line fault, and the double line to ground fault. So if we proceed to the symmetrical three-phase fault, this is a condition where either all of the phases of the system are short-circuited to each other. So anong mga instances, no? Parang let us say may malaking sabihin natin malaking branch ng or leaves ng tree, coconut trees ba, ang lawak, no? Sabihin natin nakapag-touch ng tatlong parang instantaneously nakatouch sa tatlong bare lines, overhead lines natin. So that is an example of a three-phase fault. So we have this. For the analysis of the three-phase fault, the fault currents are balanced. So this symmetric kasi. So this means that we will only consider the positive sequence network when calculating the three-phase fault current. So pag ganito yung equivalent na circuit natin, parang i-short lang natin itong voltage which is in series with the fault impedance. So ito ngayon ang mangyayari pag isosolve natin ang fault current. What we will get is the pre-fault voltage over the fault impedance. Now, for asymmetrical faults, we need to know the symmetrical components or the sequence networks. So, unbalanced three-phase systems, as we all know from a review of our power system analysis, the unbalanced three-phase system can be split into 3 balanced components. One is the positive sequence, negative sequence, and zero sequence, no? So this is actually illustrated by this. Suppose we have, we call this, say, voltage A or current IA. Makita natin, unbalanced siya, no? Now we can resolve this into a positive sequence, which is a voltage equal in magnitude and displaced by 120 degrees, of which the sequence will be ABC, no? ABC sequence, no? If we look at our diagram, so ganito yung ano niya, A1, then we have here the C, which is 120 degrees leading compared to A1, while B1 is lagging from the A1, or when we say here the voltage VA1. So baligtad yung ano natin, negative sequence. So naglag na naman yung VC2 while VB2 is leading by 120. And we have the zero sequence wherein nakita natin ang equal magnitude and direction. Equal magnitude and direction. So yan ang ating zero sequence. So when we add up this one, our V sub A, or A, we just call this the matrix A because it will stand for either a current or a voltage. So kung sabihin natin V sub A, so then this will be VA1 plus VA2 plus VAO. And V sub B is VB1, VB2 plus VBO, while V sub C is VC1 plus VC2 plus CO. So this will now be the decomposition We can express this one in terms of the sequence components, no? We can express all the sequence components in terms of the quantities for a phase using the properties of rotation, yung 0, 120, or 240, no? So if we define A as 1 angle 120, ito na ngayon ang kaniyang transformation. So in matrix form, we can have this relation of our unbalanced voltage or current in terms of the symmetrical components, sequence, voltage, and currents. For the network equations for the sequence components, ito yung mangyayari, no? The generated voltages in the transmission system are assumed balanced prior to the fault, so that we can place this E sub F here, or we can solve for the sequence voltages in terms of the sequence currents. So kinuha ko dito, like in this case, ang VEO natin, or the serial sequence voltage, is equal to the negative of ZO times IAO. So kung i-put natin into a network in a diagram, ito yung diagram niya, no? So kung ang arrow dito is positive, this is our V sub O positive, and this is the negative part here, then the current is from going from the negative terminal to the positive terminal. So this is the ZO, or the zero sequence network, and aside from that, this is the positive sequence network, a voltage in series with the positive sequence impedance, and this is now the positive sequence voltage. Okay? So ang mangyari dito, given the positive sequence network, negative sequence network, zero sequence network, kung gusto nating malaman ang case, no, inong tatlong asymmetrical faults natin, yung single line to ground, double line to ground, at saka line to ground, i-ano lang natin ito, parang pagsama-samahin natin ang ganito, i-reconfigure natin, like makikita natin in the next slide, or in the following slide, that for single line to ground fault, for a single line to ground fault, itong positive sequence network natin will be connected in series with the other network, no? So positive sequence network in series with negative, in series with zero sequence network. Then if i-close natin, pag wala siyang fault impedance ng ano natin, we will say, for example, yung in the case of single line to ground to fault, kung ang tree natin, i-assume natin zero yung fault impedance niya, ayun, tinatawag yun na bolted single line to ground fault. Okay? So we have here also different single line diagrams for sequence networks in the case of generators, no? Specific na tayo dito. So for a generator, we have voltage here in series with the impedance, generator impedance. Then sa negative sequence niya, ito yung network niya, at saka sa zero sequence. Now for transmission lines, iba-iba yung ano natin. We have the case of usually ito yung ano natin sa transmission lines. Now for the transformer, for different configurations, we have YY, the YY, one grounded, all grounded Y. So meron tayong specific na diagram for our sequence network, no? Particularly dito sa ano natin, sa zero sequence na ano natin. Okay. Now little the asymmetrical fault medyo mabilisan lang ang ano dito, limited kasi yung time natin. And I think meron naman tayong knowledge prior to this sa pag-solve ng ano natin or pag-intindi ng short circuit studies. So this is just a review. So ito yung situation pag meron tayong single line to ground fault. So as an example for this yung sinabi ko, during storm, we have a tree touch branch or leaves of trees touching at bare conductor. So, okay. So, makita natin yung positive sequence dito. Ang negative sequence at zero sequence are connected in series. And we have here a certain inclusion of the fault impedance. Pero pag zero ito, ang tawag natin dito will be now a bolted single line to ground fault, no? So this is now how it will be calculated. First of all, we will solve for the voltage here, the fault current. Ano lang muna, we will solve first the sequence current IA1, which is the same as IA2, which is the same as IAO. So, ang answer will be BF over Z1 plus Z2 plus ZO plus 3ZF. Now, the fault current will be the sum of the sequence currents. So, ipagsama-sama natin ang IA1 plus IA2 plus IAO. Dahil sila ay equal, makikita natin yung 3, the factor 3 here. So, this is now the fault current for a single line to ground fault. Now, for the line-to-line fault, ang mangyari lang, separated itong IAO, ang mangyayari, ang positive sequence at negative sequence network are connected in parallel. If there is an existing fault impedance, this will be connected between B1 and B2. But when this GF is 0, in the case of a voltage line-to-line fault, parallel na yung positive sequence network at saka negative sequence network. And this is IF, the fault current, square root of 3, my factor is square root of 3, BF over Z1 plus Z2 plus ZF. So, formula ito for the double line to ground fault, ito yung mangyari, no? So, an example for this will be yung branch ng tree nag-touch ng dalawang conductor. So, ito yung double line to ground fault. For the sequence current for this, makikita natin ang IA1 will be the pre-fault voltage divided by Z1 plus Z, the Z1 plus Z2 plus ZO plus ZF. So, if we will go in details matagalan tayo. So, I'll just get the IF. To solve for IF, we will just simply add IAO plus for IA1 plus alpha IA2. So, IAB, in this case, will be the fault current. Now, for a very important thing that we should know also is the fault level calculation. Usually, when we have an industry, for example, or let us say a utility, for example, yung sa Sipalco, no? They should know the fault level looking at their utility, no? So, titingnan din natin ang fault level ng system natin, no? In a power system, the maximum fault current or fault impedance that can flow into a zero impedance fault is necessary to be known for switchgear solution. So, the MV fault here is the fault level at a given point in MVA. If I base is the rated or the baseline current, short circuit line current flowing on the fault, we want to solve for the fault MBA. So this is now the fault level, the ratio of the uh, this is the short circuit MBA over the base, no? So we have here square root of 3 IEC or the IEC per unit natin, no? In terms of the impedance, the impedance here is the fault level in per unit. This is 1 over ZPU, which is just simply looking at the fault MBA, which is equal to the fault level times MBA base. So usually ang tinitingnan natin dito yung impedance ng per unit impedance ng utility natin, no? So this will be simply kung i-cross multiply natin ito sa fault MVA, our Z per unit will be MVA base over the fault MVA. Kailangan natin ito sa pagsusolve natin. Hindi kasi tayo magdidirect, no? Diretso ng pag we have say for example a certain industry, titingnan din natin yung remaining equivalent impedance network sa ano natin utility na nagsusupply sa atin ng electricity. So ito yung gagawin natin. We will just to understand our short circuit studies, mas maganda kung we will be looking at a typical distribution system, or lagay natin from standpoint doon sa ano na sa isang industry or a commercial system. So here we have a typical system that has distribution that has a one line diagram in the next slide. So we have to determine the magnitude of fault current when a 3-phase fault occurs at the buses. Ito yung ginagawa kong ano basis sa ano natin, because most of the time ang though sa ano no sa if you wish to apply for the PEE, kailangan natin i-solve lahat, no? At least we know how to solve the so-called shunt faults, but in determining like we will look at the worst fault that occurs in the system, and usually this is the three-phase fault, no? So we determine then the CAIC rating of the circuit breaker. So ito yung ano natin system. We have a 69 kV line from the Transco, and then it is now transformed to the 13.8 kV, no? Parang papunta na ito sa isang industry or a commercial system. Tapos we can have some loads taken from the 13.8 kV, but we will only consider we will just place this as a static load. We go further by trying to extend this to the low the 2000 from 13.8 to 2400 or 2.4 kV. So dito na nakalagay yung mga load natin na mga motors, no? So when performing short circuit studies, tinitingnan din, let us say for example, yung tatlong points ang ano natin, a certain point that is on the 69 kV side, a fault point on the 13.8 kV side, and a fault point on the 2.4 kV side. So first and foremost, we should know the impedance diagram of our system. So since we only tackle on the three-phase fault, yung positive sequence lang ano ang itatakol natin. Okay. So this is now the equivalent positive sequence impedance ng ano natin, no? So take note, ang entry point natin dito is we have the transformer here. From 69, ito ang nag-represent ng 69 to 13.8. Then a certain impedance on the line, and we have now again another transformer reactance here. This is from 13.8 to 2.4 kV, and the three machines or loads, motor loads that are considered here, no? So ito yung tinitingnan natin from 69 to 13.8. Tapos punta tayo dito, meron siyang line with a certain conductor size, and of course ang load niya at 2.4 kV itong ano natin, mga motor. This is a machine, in this case a generator, no? Aside from the grid, meron pa siyang generator dito na nagsusupply din siya dito sa ating mga loads. The loads here is assumed to be static, itong sa feeder 1, feeder 2, feeder 3. So ito pala ay mga generators. Okay? So ang mangyari dito, ang assumption natin is a system based on 15 MVA, transformer 1 at 69 kV, no? So gagawin nating analyze natin by per unit. So bawat ano natin, this should be based by sa 15 MVA at transformer 1, which is on the 69 kV side. So ito yung mga representation niya. This is now the equivalent, parang ito yung equivalent ng ano natin, representation ng utility at saka yung equivalent short circuit MVA, no, which was determined in terms of the utility impedance, no. So ito din ang mga generator reactances. Now for the simplicity at approve naman yung ano natin, ang gagawin natin, ilalamp up natin itong mga voltages so that our system voltage, the pre-fault voltage natin is set to 1.0 per unit. So ang mangyari, ito na lang ang mga impedance natin, no? So we have here the impedance XU. This is from the utility side. Kung baga sa ano natin, ito yung sa transco side, then ditong banda, ito yung sa industry natin na mga components. Okay, for the utility impedance, as we all know, yung sa fault level na may given naman siya na short circuit MVA na 535. So ang MVA base niya is 15. So we have here 0.028 na per unit. So ito, importante ito, no? So then the transformer XT1 will be 0.0694 after computation. And then the transformer 2, we have 0.228. Generator impedances also. Just to take note lang, kailangan nating malalaman kung paano ba i-change natin from a new per unit, from an old per unit to new per unit, no? So dapat alam natin ang pagdidetermine dito. So hindi ko na itatakol ito kasi sa mga basic na computation ng short circuit analysis na tatakol naman ito. X2, X3, and X4. And for the line impedance, circular miles copper, this is now the equivalent G sub L. So how will we determine the fault at bus 1 at the 69 kV side? So for bus 1, we should first, ito na equivalent niya, default at 1.0 pre-fault voltage niya. Dapat malalaman natin ang equivalent positive sequence impedance looking at the fault point. Now, kung titingnan natin ito at bus 1, meron siyang nakalagay dito na XU. And on the other side, ang XT1, ZL, XT2 which are in series. Then, yung combination nito is in series with the parallel combination ng X2, X3, and X4 of the machines. So, to solve for Z1, we have to know the parallel of the utility impedance with XT1, ZL, X62, and the parallel of X2, X3, and X4. So, ito yung magiging simplified na positive sequence impedance looking at the fault. Mag-iiba ang value nito pag dito na sa bus 2, pa-downstream, this is at the upstream, then downstream siya sa dito sa bus 4. Okay? So, computing this, we will get a fault current of 36.91, and that point 36.91 fault current per unit will be multiplied by the base current. So the base current is the base MVA divided by 1.732 times 69K. We can get the 4.63 kilo amperes. Now the minimum, maybe if we can have 5 kilo ampere kaik, then we can select this 5 kilo ampere na circuit breaker kaik rating. So yan ang makikita natin for a fault looking at bus 1. Now dito sa 13.8 kV sa bus 2, ang mangyari dito sa kaliwa, we have XU and XT1. Then sa kabila, sa right side is GL, XT2 parallel with X2, X3, and X4. So we get here 0.0864 for our Z1, and solving for the fault current is 11.57. So we have fault current is 7.261 kiloamperes. Maybe we can select a kaik rating of 10, no? So that's that is for our fault at base bus 2. Now for the 2.4 kV, dito tayo sa bus 4. So on the left side, XU, XT1, ZL, and X2 is in parallel with X2, X3, and X4. So we will now get 0.203. Take note, this is on the 2.4 kV side. The value of 4.94 will be multiplied by the base current. This is 15 MVA divided by 1.732 times 2.4 kV. So this gives us 17.8 kiloamperes downstream. Sa bus 4 natin, this is downstream na 20 kaik ang kailangan natin. Okay? So this is how we solve. Hindi ko na inano yung kinocompute yung positive sequence kasi ang worst fault natin sa 3-phase fault, makikita naman natin na pwede na natin gamitin ito in determining our kaik rating of the circuit breaker. Now, I will just show to you a simple way of validating our computation. I introduce here the solution by PowerWorld, no? Software. So ang ginagawa lang natin dito, nagdraw lang tayo ng system natin. Ito yung representation ng utility side natin sa Transco na side. So we just represent this by a generator having a pre-fault voltage of 1, and then connected here will be the 69 to 13.8, and then a line, then the 13.8 kV to 2.4 kV, and the three machines here or generators that are on the bus connected at the bus 4. So hindi na lang natin inilagay dito yung mga loads, no? Kasi for full studies, yung representation ng load natin will be static. So wala. But if there is a motor na i-consider natin pag may induction motors or mga motor loads, yun, siyempre ilalagay natin doon. Okay. So this is now the diagram, and if I will proceed, dito mayroon kasing fault analysis na ano, no? Pag i-click natin ito, automatically papunta ka dito sa kanyang environment. Check dito yung bus fault. Ano bang gusto natin? Of course, sa shunt fault, 4 lang itong single line to ground, 3-phase fault, line to line, at double line to ground. Now, selecting 3-phase fault at bus 1, sabi natin. So, pag i-calculate natin yan, calculating the fault here will give us, in terms of the magnitude sa fault natin, which is very similar to what we have done, 4.6 ang kiloamperes natin. No? So we will naging computation natin manually. No? Now, baka magtanong kayo, why I need to validate this. No? Now, say for example, if we wish to apply for PE also, it's good na parang yung may validation yung pagko-compute natin ng manual, no? So pwede naman I think the board just for the sake of validating your computation, para mas makita talaga na tama yung ginagawa natin na manual computation ng faults sa natin, sa short circuit analysis natin. Okay, and then we have for 3-phase fault at 13.8 kV side. So same procedure, if we will calculate that one, makikita natin yung 7,200. So very similar din sa computation natin, about 7,300. So you can select here ano yung available na KAIC rating ng CB. I just place here the 10 as our KAIC rating. And then for the bus 4, 3-phase fault, we have 17.7. So, pareho din, no? It will give us 20 kiloampere interrupting current. Okay? So, actually, ito yung overview ng short circuit analysis natin, no? As far as it goes, ang kino-consider lang natin yung sa 3-phase fault. But if you want, as an exercise, you can also do the case for the single line to ground fault at line to line and the double line to ground fault. Okay? So, that's all for the first part. I think I still have time. Just 15 minutes, no? Ano ko na lang ito, if you want to have a survey on this voltage drop, just parang participation nga din. So, ang question dito, in a distribution network, which of the following is the reference voltage for the voltage drop calculation? So, you can answer either maximum, nominal, rated, at saka supply voltage. So I'll just answer this and then I submit. At least meron tayong record on, no? Okay. So again, I will have to place for a while so that it will be very easy for you to interact I will just place here in the chat group, the chat box, copy, and then so you may answer from there, no? So ano ba yung we will look for distribution network. We will be governed by of course, by the Philippine distribution code. So ito yung ano natin, code natin, and maybe we want to determine the result if you started answering it already, no? So before we dig up in depth the voltage drop calculation, which is another way, no? We have a way of solving the voltage drop very similar also using the Philippine Electrical Code calculation, but I will introduce here another method of solving, particular in a distribution system. So ito yung answer natin, 33% based sa nominal voltage. Ang higher natin dito sa supply voltage, no? So I am expecting solution, an answer like this, because nakasaad sa ano natin, siyempre ang reference natin from our Philippine Electrical Code will be the supply voltage, no? Clear naman siya sa Philippine Electrical Code. But for a distribution system then, ang nag-govern na reference natin will be the nominal voltage. But in some cases, ang nominal natin parang magiging ano din siya supply voltage eh. So usually we define here the nominal voltage as ang nominal value niya for a certain class of or a size ng system natin. Let us say for example, for a 69 kV system, pwede man ding mangyari na ang supply din natin is 69 kV. No? So ito yung kino-consider sa yung nominal voltage. This is the reference based ano natin sa Philippine Distribution Code. Of course, ang supply voltage, ito yung sa Philippine Electrical Code. Okay, so let's start with our discussion with the voltage drop calculation. Now, based on the PDC 2017 edition, this was already made as a resolution. So, for the voltage variation, in this case, we consider a short duration. Some definition shall be defined as the RMS value of the voltage from nominal voltage for a time greater than 1/2 cycle and not exceeding 1 minute. So this will be some definition. Voltage well will be a description for an RMS value of voltage increasing between 110 and 180% of the nominal value. And then a voltage sag, if the RMS value of voltage decreases between 10% and 90%. So this is the definition from our PDC. And then the long duration variation, this is greater than 1 minute. So mo na ning gitawag nato nga under voltage. So specified siya sa PDC, plus minus 10% lang siya, no? Plus minus 10%. So important also in the section 3.4 here that distributors shall ensure that no undervoltage or overvoltage is present at the connection point of any user during normal operating conditions. Thus, ito yung importante na kailangan din natin. There is a wisdom of why is it important to determine the voltage drop, no? Especially when we will be analyzing our system. So, na-discuss ito ni Engineer Eric kanina, yung pag-determine ng voltage regulation, from a simple circuit, we have here the load from the supply or the sending end voltage to the load voltage. So if we have this phasor diagram here, we regard this part here, the IZ as the voltage drop, no? And of course, our definition for the regulation will be the difference of the supply or the sending end voltage and the load voltage over the sending end voltage. Okay? Now for the voltage drop, so of the source and the load, no? So sa supply at saka sa load natin. So this is the voltage drop. Another definition, this is the real part of the impedance drop. Okay? Now, for the line impedance, for determining in a certain distribution system, particularly sa overhead lines natin, parang pare-pareho lang, no? Yung example for this is our system ng ano namin, university. I base this as my example kasi inside our university we have bare most of our overhead lines are bare ACSR at 13.8 kV. So sa whole campus mayroong nagraran doon na 13.8 kV. And it is important to determine the impedance. We all know this in our power system analysis and determining the impedance of a line. And we have here considering the configuration for our three-phase line, which is usually configured horizontally yung mga conductors natin, no? So we come up with the equivalent, which is the cube root of DAB, DBC, and DCA. So the GMR is the geometric mean radius, which can be determined from tables. Anyway, these are given, and we can determine this. In this case, we have an example which is a 2.5 feet ang spacing niya, no? 4.5 feet horizontal space sila. So this is DCA, which is 7. So the conductors is 336 400 ACSR. So finding the passive sequence impedance, we will get 0.306 plus 0.6272 ohms per mile. Now, I introduce here the key drop factor, which is defined as the percent voltage drop divided by the kVA mile. No, the kVA which corresponds to the load at a certain area, and miles is the distance. No, so the key drop factor is determined by computing the percent voltage drop down a line that is 1 mile long and serving a balanced three-phase load of 1 kVA. So this is our definition. Now, for example, we want to compute the key drop factor assuming a load power factor of 0.9 leading a nominal voltage of 12.47 kV line to line. So the impedance of 1 mile will be computed kasi kanina ohms per mile yun eh. So times 1 mile, we have this the 0.306 plus 0.6272. And the current taken for a 1 kVA at 0.9 lagging power factor with the nominal voltage of 12.47 is 0.046. So if we determine the voltage drop can be determined by the real part of the impedance and the current times the current. So this is now the voltage drop. Nominal N and nominal line to neutral voltage will be 12,470. So the K factor will be 0.025408 over 7199.6. This is a way of determining, because this will be a factor, a K factor. If we will multiply this by the load on that part of the system and the length of the line, so pwede na natin na makuha directly ang kanyang voltage drop, no? So for a certain segment in the distribution network. So we will apply this in this case, no? So the application of the K-drop factor is not limited to computing the percentage voltage drop down one line segment. When line segments are in cascade, the total percent voltage drop can be from the source to the end of the last line segment will be the sum of the percent drop in each line segment. Okay, so this is the problem. Here we have a phase conductor 40 ACSR distributed from 0 to 6, no? Kung dito yung upstream niya papunta dito sa 6 sa downstream niya, titingnan natin kung ano yung voltage drop when it goes to this last or dito sa downstream side, no? So first we will determine with this horizontal spacing na ano natin, the series impedance, the K drop, and the total percent voltage drop to node 6. So ito lang. For the solution, we will solve for the Z. The Z here is 0.592 ohms per mile plus J 0.7946 ohm per mile. The K drop will be after solving for the voltage drop. So we have here 0.0051 distributed along the line, no? So 0.0051% per kVA per mile. Okay, so this is now the situation and finding the total percent voltage drop from 0 to node 6, no? So tingnan natin yung segment NO2 o bus or node 0 to node 1, yung segment na may length na 0.15 mile. So yung K-drop factor natin, imomultiply lang ng 0.15 times 1675 kVA. The 1675 kVA from 0 to 1 will be ang sum. The sum, kasi dito sa upstream, ito yung sum ng load natin. So if we sum up this one, this will be 1,675 kVA flow. So ang voltage drop dito na point at node 1 will be 1.281. So between N1 and N2, we have now 0.175 mile. Ang i-subtract natin itong 200 from 1,675, ito na, 1,475. So the result here is 1.316. Going farther, at N2, N3, we have 0.2 miles. Subtract 350, magiging 1,325 siya. So the voltage drop here at this point is 1.352. Okay? Then going N3, N4, N4, N5, and up to node 6, we can now compute the total drop at this point. So the total drop at this point will be 6.110. So if we will look at our this passes sa atong Philippine Distribution Code, because ang variation na sinabi natin is 10%, plus minus 10%. So this is within the 10% variation. So this is how we simply an alternative way of finding the percent voltage drop for our distribution network. And with this, time is already running out. I'll thank you for all your participation and for listening. Thank you.